Welcome to week 7. We're going to cover area moment of inertia of composite bodies. So the area moment of inertia, it's a property of an object based on its shape, and it's used to predict how that object will deflect, bend, or how it will react when we apply stress on it. Typically, we deal with beams in mechanics, and the units here are a distance to the 4th power, so a meter or a millimeter. Each different shape has its own equation for area moment of inertia, and that there will be a table in your book for that. But most often we deal with rectangles, so that will be 1/12 base times height cubed. The other formula we need to know is the parallel axis theorem, which is used to find the overall area moment of inertia of a composite body like this one or this one. And we should know a composite body is just a body that's made up of subcomponents. So this one is made up of 4 different rectangles. So the parallel axis theorem basically states that the overall area moment of inertia of the composite body is equal to the individual moment of inertias of each component plus area times distance squared, where the distance you're accounting for the difference in the neutral axis. So let's look at this body. Overall, your neutral axis may be somewhere here, but each component has its own neutral axis, which is located here for this one or here for this one. So you're accounting for the difference in the location of the neutral axis. So let's look at this example. A beam is constructed from 3 boards bolted together. Determine the moment of inertia of the body. So we have this overall composite body composed of 3 different boards. The first thing we want to do is find the neutral axis, or y bar, of the composite body, and then use the parallel axis theorem to calculate the overall area moment of inertia. So I chose to reference everything from the top because it makes it easy to calculate these distances later on. And here I have 2 identical rectangles and 1 different one. I outline each of their neutral axes. So a rectangle, the neutral axis is halfway down the rectangle, right? And this goes back to last week's video, finding the neutral axis. So I took the area of every rectangle, y bar of every rectangle, y bar times a, and in the end I do y bar times a divided by a, and that tells me that my neutral axis will be 186.8 millimeters from the top. So this is kind of the center of gravity along the y-axis of this composite body. Now I use the parallel axis theorem. So remember that this I is basically 1/12 base times height cubed for every rectangle in the body, and then a times d squared will account for that later. So I start by just looking at the 2 identical rectangles, and I multiply by 2 and 2 here because there's 2 of them. Everything's going to be the same for them. So I start with 1/12 base. The base is 25 millimeters times the height cubed, and the height is 250 millimeters. And I converted them in meters, but you can use millimeters. It doesn't make a difference. Plus the area of the rectangle, which is 25 times 250, times the distance squared. This distance is basically the distance from the neutral axis to the center of gravity of the body that you're looking at. So it'll be this short distance here. And to find that, you just take the neutral axis, 186.8, minus 250 divided by 2. And that will give you your d squared. So now that we've accounted for these 2 rectangles, we look at the last one that we haven't accounted for yet. So 1/12 times the base, which is 25, times the height cubed, which is 350, plus the area, which is 25 times 350. And then the last thing we look at is the distance from the neutral axis to the center of gravity of the rectangle we're looking at. And how do you calculate that? Well, you know where the neutral axis is located. All you have to do is find the the distance from the top to here, and that ends up being 275 millimeters. So I do 275 minus 186.8, and that'll give me this this distance here, this difference in distances. And then I square that, and overall I end up with my area moment of inertia. And it's pretty straightforward. Just make sure that you're accounting for the correct distances. Whenever you're trying to find d squared, make sure you know what you're looking for. It's the neutral axis to the neutral, so the overall neutral axis to the neutral axis of the component that you're looking at. And that's it.